Hello, everyone. The following is the first in a series of lectures covering Chapter 38. Today, we'll be talking about the single slit diffraction pattern. To begin, there's a little storyline to this chapter as presented by the textbook. Here it goes. You are in a football stadium watching the marching band doing their pre-game performance. As the band marches toward your position, you enjoy their rich, well-blended music. Then the band turns around and marches away from you, and you say, "Wait a minute. You can still hear the clarinets and saxophones, but the trumpets and trombones have become very quiet." Why does that happen? You're determined to keep your mind on football today, so you set that phenomenon aside. You sit back in your seat, and while waiting for the game to start, you put on your polarized sunglasses. You try to ignore the nagging question in your mind about why sunglasses should be polarized. The fact that it must have something to do with physics creeps into your mind, and you pull out a pencil and a piece of paper. The football game begins, but you are drawing diagrams of waves. So we'll talk about what's going on in this scenario a bit later into the lecture, but just presenting the story now for some real world context into why we talk about diffraction and polarization, which are effects that can happen to waves, including light, and how these have sort of implications for real world objects. They're not just very niche science experiments, but rather things that occur, such as with optical instruments. Diffraction tends to limit how well you can see things. So on with the actual lecture. Now let's recall that last chapter we talked about Young's double slit experiment, where you cast the light into two slits and then the light gets diffracted and you see a pattern on the screen created from the interference of the diffracted light emerging from both slits. So if you have one slit or you have multiple slits, such as a diffraction grating, the pattern is different, but still retains some similar features, such as the number of fringes. The location of them will remain the same if all you're changing is the slits. But overall, it turns out that even a single slit creates a pattern because the interference of light still occurs when it diffracts through a single slit. So we're going to start off with the pattern produced with a single slit, and we'll see how, as you add more slits, you actually create a more complex pattern because there's interference that happens due to light passing through just one slit, and also interference that happens from the light passing through different slits. So there's actually two patterns happening at the same time, the diffraction and interference. So, as we said in chapter 37, diffraction is simply an effect of light, particularly one that can only be explained with light's wave like nature. And simply, it occurs when light or other waves can do this too. Sound waves and water, ripples in water can also diffract. But basically, when they pass through a small opening or even a small obstacle, or even like a sharp edge, the wave sort of becomes anew. It sort of begins from the other side of the obstacle or from the other side of the slit as a point source. So it's like a new ripple gets created on the other side, and that's diffraction. The general idea is that we're seeing the waves passing through an obstacle that's much bigger than the wavelength, and if you have some kind of screen on the other side and you're casting light through a slit, then you get to see how light gets diffracted by looking at the projection. If you have a wave like water, you can actually see the diffraction right away through a screen, like in the pictures at the bottom here, where water is running through different slits of different sizes, and you can kind of see how passing through each slit, you see the diffraction there. The smaller the slit, the more noticeable the diffraction is, right? You can see how past the barrier, um, all the ripples emerge from the same point from the slit. So obviously you can't necessarily see how the ripples emerge on the other side of the screen, on the other side of the slits, I mean, with light, but you can put a screen on the other side and see light there projecting on the screen. And much like in the double slit experiment, you get to see this pattern of light and dark fringes. And this pattern is called a diffraction pattern. In the case of the double slit experiment, what you actually get to see is a combination of a diffraction pattern and an interference pattern. But when you have a single slit, all that there is the diffraction pattern getting projected. And what's notable about this pattern is that there's generally a bright central fringe, the central maxima, and then you have this sort of like neighboring, this alternating light and dark fringes. And as you move farther away from the center of the screen, the maxima diminish in intensity. Just like in the image here, you see the diffraction pattern has a broad central fringe, narrow dark fringes, which you can call the minima. And then you can see how the neighboring bright fringes, which are called the side maxima, get fainter and fainter as you move away from the center. Another example here is the diffraction pattern when you shoot a light through some small edge where it's only on the lower half of the screen. Some object covering it. It's just a small sharp edge in the middle. So you get this half of a diffraction pattern where light diffracts over the small edge, and below the middle where the object is, light gets blocked, but light diffracts around the edge, and you end up with this pattern here of fringes just in the upper half of the screen where light can go. And you'll note, right, that there's a big central fringe, and then there's a series of fringes that get smaller and smaller, kind of get squished together. So why does this happen? Well, the the reason it happens is actually interference, but the nomenclature is still called the diffraction pattern. So the diffraction is what happens when light passes through the edge of the slit, and the actual image that gets projected on the screen of light and dark fringes, that image occurs due to interference. We'll talk about that in a little bit, but here's an image of how diffraction can happen when light passes through a small object. So this is the diffraction pattern, a high resolution image of the diffraction pattern caused when you cast light into a penny. And this is what you'd see on the other side of that penny. Now, most of the light sort of doesn't get to project right behind the penny, but you still see this diffraction pattern. No, you still see that right on the other side of the penny, in the center of the screen. There is like a tiny bright spot, and most of the area surrounding it, where the penny is, yeah, it's just shadow, it's just darkness, and then beyond that, you see this circular diffraction pattern. So this sort of study of diffraction through small objects was beginning to be observed, to be performed in the early 1800s. Thomas Young did his double interference experiment in 1801, and the pattern that he saw, right, can only be explained through interference, through understanding light as a wave. But even then, there was still a lot of skepticism about light being a wave. despite the fact that what Thomas showed was something that could only occur if light was a wave. So ray optics, where light travels in a straight line, could be a particle. Doesn't explain what the double slit experiment saw, but still, people were not convinced. So there was a competition established by the French Academy of Science to establish the true nature of light in 1818, and Simeon Poisson, who was all in favor of ray optics. Now, this is the same person who developed the distribution that we now call the Poisson distribution. He argued that if light were a wave, then you should be able to cast it onto a circular object, and in that object's shadow, you should see a central bright spot. Also, right, that like you should expect to see some diffraction pattern around the edge of the object. And Poisson said that no, this is obviously absurd. If we actually do this, if you cast a light over a small object, particles of light would just get blocked, so you never see a bright spot in the center of the shadow. At the time, with the tools and technology they had yet to see a bright spot in this sort of setup. But Dominique Francois Jean Arago, who was the head of the competition, he performed the experiment that Poisson was talking about. Who Poisson was very skeptic. He said that no, you're not going to see this bright spot because light's a particle. But Dominique did the experiment, and they did actually observe a bright spot at the center of the shadow. So this bright spot, much like the pattern seen by Thomas Young, can only be explained by interference of waves, and ray optics could not explain it, giving more validity to the wave theory of light. So let's diffract light through a single slit, kind of like a double slit experiment, but now we just have one slit. So we have a screen, we have a slit, and we are sending coherent light into the slit. So few parameters here. The slit is a distance L from the screen, and the width of the slit is called A. So with this experiment, much like the double slit experiment, we can actually find out what the wavelength of light is by configuring our parameters. So you cast light through this little slit, and the image that gets projected on the screen is the single slit diffraction pattern that gets the name the Fraunhofer diffraction pattern. Again, defined by the general shape of diffraction, which is a central bright fringe and a surrounding alternating light and dark fringes. Now, when you had two slits, right, light from both slits interfered with one another, creating the pattern. But here, we also see a pattern despite the fact of there only being one slit. So, why? Why do we see a pattern when light's just coming from one place? That's because, while there is a single slit, it's not that the whole slit is a single point source. Every part of the opening acts as a point source. So remember Huygens' principle. Each portion of the slit, so if you zoom in on the slit, each little point in space acts as a source of light waves. So there's light emerging from all points on the slit. And so interference can occur between any of those points. So there's particular areas right along the projection screen where the points on the slit, all these point sources within the slit are interfering with one another. So the slit basically interferes with itself. And then you can actually derive, using the geometry of your lab setup, you can actually derive the location of all your dark fringes on the screen along the axis of that screen. So basically, it turns out that the points where dark fringes occur, you can figure them out based on just the width of the slit and the wavelength of light you're shining through. So we have a formula then for figuring out the angle from the center of the screen to the dark fringe based on the order of that fringe. So the formula here um, gets you to specify what order of fringe you're looking at, and the idea is that they're measured from the center and then away from the center. That's why the first order fringe would be the two dark fringes right next to the central fringe. Note that there's no order zero, because order zero will be the center, but in the center there's always a bright fringe. And what this formula also tells you is that the angular position of the dark fringes increases when you send light of bigger wavelength. So the pattern gets wider as lambda increases, and it gets narrower as the slit width increases. So if you make the slit width A really, really big, the pattern's gonna get crunched together in the center of the screen. So let's put it to the test. Let's suppose that we have the single slit diffraction setup here, and the slit width gets cut in half. So what happens to the bright fringe? Well, remember the bright fringe is surrounded by dark fringes, so you just kind of look at the change in their angular position. If you look at the formula, if we reduce the slit width, the angular position of the dark fringes overall increases. So if the angle at which the dark fringes occur increases, that means that there's more room for the bright fringe in the center, which means that it's going to become wider. So here's a problem here from the textbook. It's pretty self-explanatory, but it's worth pointing out what they're asking for here is the vertical position. So the relationship between the angle of the dark fringe and its vertical position is with the sine function and the length, necessarily the distance between the slit and the screen, because that will get you using the sine function, and gets you the vertical position as measured right from the center to the dark fringe. And in this case, you're looking for the width of the central fringe. So you just take the position of the first order dark fringe, multiply it by 2 to account for both sides, and that will get you the width. In this case, the slit is about a third of a millimeter, and that gets you a bright fringe that is pretty small. If the width increases, then the fringe will become smaller, so it decreases by a factor of 10. So in a lab setup, right, you can play around with the width of your slit so that you can more easily measure the fringe pattern that occurs. The smaller the slit, the bigger the fringe pattern. So you can also describe the intensity of the diffraction pattern as you move along the screen. And this formula is based on the idea that there's a max intensity that occurs right at the center. So that's as bright as the pattern's ever going to get. And there's two things happening: that as you move away from the center, the intensity keeps kind of cycling through bright fringes and dark fringes. So there's this maxima minima occurring. But overall, as you keep going further away from the center, the intensity drops off altogether. So the height of the peaks of the maxima gets shorter and shorter as you move farther away from the center. So the formula for the intensity of the pattern projected from light passing through a single slit is shown below here. And basically, there's a term right outside that accounts for the maximum intensity, that at the angle of 0, all you get is that max intensity. But then there's a term here, there's a sine function with a sine function inside of it in the numerator. And this term is just there to account for the series of maxima and minima. It accounts for the fringe pattern as you move around the screen. And there's a term at the bottom that basically accounts for the fact that intensity falls off as you move away from the screen. So remember the double slit experiment? What were we seeing back then? It turns out that when you cast light through two slits, the pattern that you see is actually a interference pattern enveloped by a diffraction pattern. Now, usually this pattern is pretty wide, so you only really get to see the central fringe, the central part of the diffraction pattern on the screen. Therefore, you only see the fringes, you only see the interference fringes within the central fringe, and that's what Thomas Young saw, and that's what you just get to see in the lab if you were doing the double slit experiment. So you don't really notice the big diffraction pattern that goes on. You should see the interference pattern occurring from the two slits. It's worth pointing out that if you were to shrink the projection, if you were to like bring the screen a lot closer to where the slit is, then you'd see that from the double slit experiment, the projection effectively has this, small-ish fringes from the double slit interference, and then this big envelope fringes from the diffraction pattern. This is kind of confusing, of course, because both the diffraction pattern and the interference pattern occur due to constructive interference. So it's a nomenclature situation where when we talk about the interference pattern, we're talking about light from different slits interfering with each other. When we talk about the diffraction pattern, we're talking about light from the same slit interfering with itself. So to talk about the intensity of the double slit experiment, you can use the formula above, which is a bit of a mouthful. But basically, the cos term accounts for the maxima and minima of the interference pattern. So this accounts for the fact that you have two slits. So normally in the lab, you only really see the central interference. You won't really see the other fringes besides the central one. And then the next term, the term in square brackets, accounts for the diffraction pattern. Now, if you keep adding more slits, you are still only really going to see the central part of the envelope. So you just basically have more and more secondary maxima as you add more slits. So these are sort of like smaller bright fringes between your regular bright fringes. The bright fringes themselves don't change position as you add more slits. They just get narrower and more sharply defined. So as you keep adding slits, basically the peaks get sharper and sharper. And again, you're only looking at the central sort of part of the envelope, so you don't really get to see the diffraction pattern. The only hint that diffraction is also occurring, the diffraction pattern is also there, is the fact that the intensity of the interference maxima decreases a bit as theta increases. And that's all for now. I hope you join me next time where we'll be talking about the limits on resolution of telescopes as imposed by diffraction.